Alright, so this is our next video on electronic structure. This will be, I think, number 4. And we're going to be looking at the next group of slides here from Chapter 3. So slides 58 to 84. Here, as you see in Dr. Russell's comment slide. And we're going to talk a lot about the periodic table and tie that back to the idea of the quantum numbers. And then there'll be some questions for you that we'll give you as an assignment in Canvas based on these. That'll help you practice these stuff. All right, so moving on down here, we are going to look at the first slide. Oops, there we go. We have our learning objectives there, so be able to predict the ground state electron configuration, be able to identify and explain exceptions, and relate those configurations back to the periodic table. All right, so we said before that energy increases as the principal quantum number increases, and we remember it also we said that energy increases, it's a function, if you will, Fn function of n and also to some extent L. And the good news about that is that we're able to use the periodic table as a very effective way to understand the relationship between those and predict the energy of the outermost electrons. You know, generally speaking, S is lower in energy than P is lower in energy than D is lower in energy than F. Remember that L has values of 0, 1, 2, 3 typically, and that corresponds to orbital types that are S, P, D, and F, and may remember that that the m sub L value can vary depending on the L value. So if L is 0, we can only have one value of m sub L, 0, and that means that the number of orbitals in the sublevel is 1. We have one orbital for every possible value of m sub L. If L is 1, m sub L can be minus 1, 0, or plus 1. That gives us 3 orbitals in the sublevel. If L is 2, m sub L can be minus 2, minus 1, 0, plus 1, plus 2, from negative L to positive L. That's 5 orbitals in the sublevel. And then if L is 3, we can go all the way to negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. That's 7 orbitals in that sublevel. And you may remember that at the number of electrons, if we have 2 electrons per orbital, that means 2, 6, 10, and 14 possible electrons in those sublevel for a given value of n and L. And so here we see the energy diagram that shows that energy relationship, where we have the S's on the first column and the P's in the next column, and you see the P's are a little higher in energy than the S's for each level typically. And then the D's in the third column and the F's in the fourth column, and you see that relationship here where if you look at the 3D and the 4S here, you can see that while n is 3 in 3D, 3Ds are higher in energy than the 4S's, so that shows that n and L relationship, again, S, P, D, and F are what tell us what the value of L is. The number there tells us what the value of n is, and that's the note down here, that note about that. There was a thing here, electrons in atoms tend to fill the low energy orbitals first. That's something we're going to learn is called the Aufbau principle. AUFBAU, that's German, and that means building up, and that we build up from the lowest orbitals to the highest orbitals. So the first 2 electrons are going to go in the 1s orbital here, and then the next 2 electrons would go in the 2s, and then we go up to the 2p, for example. So you see, and again, I'm using, when I say an arrow up, that means an electron with m sub s equal to plus 1/2, and if I say down, that's an electron with m sub s equal to negative 1/2. That's the spin quantum number for that. Now, there are 2 things that we talk about. What we're kind of looking at up here is an orbital diagram. So this up here was sort of an example of an orbital diagram. The other way we'll describe the electrons is using an electron configuration. Electron configuration has a little less information in it, but it's probably more commonly used, and it's easier to write. It takes up less space than an orbital diagram. So in an electron configuration, you have an example down here where you have, oh, this is a good one for colors. Let's do colors. Let's do, okay, green. So the part that is green here, the 1, the 2, and the 2, that's our principal quantum number. And then in blue, I'm gonna, the S, and P, that tells us the orbital type. And then with red here, where you've got these numbers up here as superscripts, that is the number of electrons in that subshell. So we're reading a lot of information packed into that, and you have to be able to decode these things and come up with these things and learn these different ways that we represent things. So practice is appropriate. So here is our hydrogen atom. The hydrogen here is depicted, basically this is you're representing your nucleus of the hydrogen atom, which is going to contain 1 proton and probably no neutrons. And then we have 1 electron, which is depicted as a particle there. In this cutaway version here, this is the 1s orbital, that region in space where that electron's likely to exist. And so we write that again as 1s1 is how we read that, where the first 1 is the principal quantum number 1, the lowest energy level there. The S is the subshell, and then the third one that we say is the superscript 1, which is the number of electrons in the subshell. So if you add up all those superscripts for an atom in their electron configuration, you're going to get the total number of electrons. So again, what we do to write these electron configurations is we start at the lowest energy level and we build up. Again, using the Aufbau principle, we build up to get there. We also obey the Pauli exclusion principle, which says no more than 2 electrons per orbital, and that they have to be spin paired, not spin parallel. All right, that's not allowed. And again, that's obeying the Pauli exclusion principle. This is a mnemonic people use to get the filling order. And oftentimes you'll see it written this way, and the idea is that you start up here and you fill the 1s, then you run around and fill the 2s, and then you go around and fill the 2p, then the 3s, and then the 3p and the 4s, and then the 3d, okay, 4p and 5s. So you get that filling level you do. You've got essentially on this side here, you've got the quantum numbers, right? So n is 1, 2, 3, 4, 5, 6, 7. This way, you've got the value of L, 0, 1, 2, 3, which we usually write as S, P, D, and F. And that's how they arrived at this chart. And then you could go through this and fill up the electron configuration from an element depending on the number of electrons they have. So they give the example down here, cobalt 27, which is element 27, right? That's meant to be the atomic number. Normally when you see something written like that, that's meant to be the mass number. But the cobalt has an atomic number of 27, which means it's got 27 protons and 27 electrons, and we're not worrying about the neutrons right now. So we put 2 of those electrons in the 1s, 2 in the 2s, 6 in the 2p. Okay, so 2 plus 2 plus 6, we used up 10 so far. 2 in the 3s, that's 12. 6 in the 3p, that is, what are we up to, 18 now. And then we put 2 in the 4s, that's 20. And now we get to the 3d, we have room for 10 there, so we don't quite fill it up. We have 7 there. So that's the way they come up with this right here, which they write it out. They kind of pause and go through it. And the reason they write it that way is to emphasize that you do the 4s2 first and the 3d7 next after that. And of course, this is figure 326 in your textbook, so you can make reference to it there. Now, the system I usually use and I prefer is use the periodic table for this. And the reason I do that is that in a classroom, anytime I'm in a chemistry classroom, anytime I'm taking a chemistry test, it's a pretty good bet I'm going to have the periodic table available to me. So if I can tie this to the periodic table, I'm going to be a lot more likely to remember it. So you see this periodic table. Let me blow it up a little bigger here. And again, these are from the notes in our shared OneNote drive. So you can see here that they've got the orbital and the principal quantum number for each part of the periodic table identified here. And what you're basically doing is you're let each box represent an electron. So let's do the one right next to cobalt. Let's do nickel, right? So if I'm looking at nickel, I'm going to have 1s2, that's hydrogen and helium. I'm going to have 2s2, which is lithium and beryllium. I'm going to have 2p6 to neon, 2p6. I'm going to have 3s2 over there, sodium and magnesium. I'm going to have aluminum through argon is going to represent 3p6. I'm going to have to continue on the next line. 4s2 is potassium and calcium. And then I count over here 1, 2, 3, 4, 5, 6, 7, 8. I'm going to have 3d8 to get the nickel. And, you know, again, in broad strokes, the periodic table is divided into these regions where we're filling the S's over here, we're filling the P's here, helium here goes with the S's there, we're filling the D's here, we're filling the F's here. The number over here, 1, 2, 3, 4, so on, 5, 6. What we have to recognize is that you take whatever that number is and put it in front of the S. We usually say NS, NP, N minus 1D. You see here we're at the 4th row, but this region is the 3D. So we subtracted 1 from it. And then the F block down here, which comes off here, they're called the lanthanides and the actinides. They come off rows 6 and 7, and here we take that number and subtract 2 from it. So 6 minus 2 gives us the 4F, right? And 7 minus 2 gives us the 5F orbitals. And if you can use the periodic table, and again, that key idea is you're letting each box represent an electron, you can just count up to your whatever element you're being asked to do. Now, the orbital diagrams, which we had a picture of before, which I sort of showed you one there, orbital diagrams give us a little more information. They take up a little more space. What we do is we represent each orbital as a box or a line, and we represent the electron as an arrow, where an up arrow is m sub s is plus 1/2, and a down arrow is m sub s is minus 1/2. So what we can do right here is we look at this picture right here. That orbital diagram tells us that for this electron, n is equal to 1, L is equal to 0 because S means 0. M sub L has to be equal to 0 because there's only one possible value of M sub L. And then the fact that that's pointing up tells us that M sub S is plus 1/2. So the 4 quantum numbers for this electron are indicated in this orbital diagram. So we have a lot more info there. Here are some more orbital diagrams as we go up in the periodic table. 2 electrons in helium, 1s2, gives us that orbital diagram. Lithium, we have 3. The next energy level up is 2s1, so we depict it that way with a separate block. So if the blocks are separated like that, that means that energy is going up between those 2 blocks. Generally speaking, as we're going this way, energy is going up. We're going to see, though, that sometimes we'll say that we have a way of saying that things are at the same energy level. So if we go down and look here, now when we write the 2 P's, if they're written together like that, that means they're at the same energy. Remember, in our previous video, we learned those were called degenerate energy levels or degenerate orbitals. Now, when we get to that situation, we run into Hund's rule. Hund's rule, basically, my shortcut version of it is don't pair them till you have to. So when we're putting our second electron in and we get to carbon, which is 1s2, 2s2, 2p2, we have 2 p orbitals, and we have a choice. We could have put the second electron in, we could have done this, or we could put it in a different orbital and have its spin be up or spin parallel to the existing one. Hund's rule says that this is not right. That's not the lowest energy state, that this one's the right way to do that. So here's some more examples, and you should look and make sure that you can agree with these and generate these, and you're going to be expected to be able to do this for any atom for periods 1 through 5, so all the way down to 2, 3, 4, 5. So basically all the way down to xenon, right, through xenon, and you need to be able to generate those. And again, we got the electron configuration there, the orbital diagram here, takes up more room, gives us a little more information. The other way, as I mentioned before, orbital diagrams can also be written going vertically. If the energy is increasing, we could write it 1s, 2s, 2p, like so. So, for example, nitrogen would be 1s2, 2s2, 2p3, and we're obeying Hund's rule. So this is equivalent to that first diagram, just a different way of writing it going up instead of going across. You'll also see other variants of it. People will use circles, and I've even seen folks indicate the electrons that way as a way of showing their pairing. You'll see parentheses. You know, they're just different books use different ways of doing it, and you have to be comfortable with all of those. Now, we're getting to a concept here that's getting close to using this to actually predicting some chemical behavior, which is really what we're trying to do. The reason we're trying to figure out how the electrons are arranged in the atom is we want to be able to explain why certain elements react the way they do, why certain compounds are stable and other compounds aren't, things like that. And so we're going to come to this concept now of valence and core electrons. So let's write an electron configuration. Let's do phosphorus. Okay, and I'm going to just do the electron configuration. So phosphorus is element number 15. So 1s, 2, 2s, 2, 2p6, that's 10 of our electrons, 3s, 2, we got 12, we got 3 left, 3p, 3, okay. When we say the core electrons, we're going to identify the ones that are in the lower, not in the highest value of n. So this is the valence electrons out here with the highest value of n. And these are the core electrons. And notice that a core electron always represents a noble gas configuration. If I was looking for the element that had that configuration, 1s2, 2s2, 2p6, that would be neon. Neon is 1s2, 2s2, 2p6. So that's that noble gas configuration thing. And in fact, what we can do is we can shortcut this to be bracket Ne 3s2, 3p6. So we're representing the core electrons using a valence, using the noble gas abbreviation, and then we have just the valence electrons here. And it turns out these guys are the ones that really matter. The valence electrons are the ones that matter in terms of predicting reactivity. For this abbreviated technique here, that core, this has to be a noble gas. You know, I couldn't, for example, say that phosphorus is bracket Si 3p1. That would not be allowed, right? It has to be a noble gas that we're using as a bracket there. So here's that shown for sodium, where we take that core. Again, it's the neon core, and the only thing outside of that core is the 3s1, so the abbreviated electron configuration is there. And then we start seeing some similarities. If you look at the groups on the periodic table, if you look at, for example, group 1, lithium, sodium, and potassium, they're all ending in S1, right? So this is all ending in S1. Group 2 is all ending in S2. Remember, the groups are the vertical part of the periodic table, so lithium, sodium, potassium is group 1. Hydrogen's there too, but hydrogen's a little different because it's a non-metal. These guys are all metals. And going on down, you've got rubidium and cesium there. When Mendeleev originally created the periodic table, you know, building on others' work on the periodic table, he arranged those groups based on their chemical properties. Now we can see that those chemical properties are explained by the electron configurations. So now we have a pretty hard to see periodic table here, which again I'll zoom in on a little bit so you can see. And you see how generally within the groups you have the same configurations. So if I go down the nitrogen group here, group 15, right, everything ends in P3. All right, lost the picture there. See if I can find that back. There we go. We're slid off to the side. That's our problem. Okay, so we're, like I said, we're looking here. If we zoom this up a little bit, make this a little bigger, we can see that everything in group 15 ends in P3. If you go down through this group, everything ends in P3, and that's why they're all similar. Now, there are some exceptions that happen in this, and we're not going to deal with those so much in foundations of chemistry. Later on, you'll see them, but there are some exceptions. So, one of the exceptions that we're going to not deal with some screwy stuff that happens with the transition metals. I mean, the transition metals, obviously we start putting those d electrons in. We've done a couple of those. There are a few exceptions, and we'll skip those. Again, also with the F level, the transition metals there, what are called the outer transition metals, or the lanthanides and actinides, they behave kind of oddly, and we won't get into that really. If you look back at this table here and you look at some of the values, you can see how there are exceptions that show up here. So for example, if you look at the chromium, molybdenum, and tungsten here, you have 5d electrons there, 5d electrons there, and then down here I think you have, well, it's really small. You have some unusual behavior around that where s electrons are getting promoted to the d orbitals. Again, in Chem 130, we're not going to worry about those. We're just trying to get the basic stuff. So here's the phosphorus example. We did that one earlier, and now that we are able to write these electron configurations, we can see this idea that elements that are in the same group have similar valence electron configurations, and that explains why they have similar chemical reactivity. So the periodic table is your guide to all this, and so some more examples here. What we call the main group on the periodic table is the S or the P block. So you remember I drew the periodic table before kind of roughly and said this was the S block, and then we have the D block in the middle, and then we have this is the S block, but this is all P block, and down here we have the F block. The S block and the P block are what are called the main group elements. And those main group elements, you know, if you're talking about S2 P6, that's going to give you a total of 8 electrons in the valence orbitals maximum, and the valence shell maximum, and that leads to something we're going to call later the octet rule, octet meaning 8. The transition metals are the D blocks, and the F block is called the outer transition metals. Now when we look at ions, what you do when you have an ion is a charged atom. We're going to gain or lose electrons. If I gain electrons, then we're going to have electrons added on. That's going to be an anion. If we gain electrons, it'll have a negative charge. And if I lose electrons, that'll be a cation, which will have a positive charge. So if we're trying to predict the electron configuration of one of these ions, what we're going to do is write out the parent atom and then add or remove the number of electrons that we need. So you might think about what these guys are going to look like and maybe pause the presentation at this point and see if you can answer these questions before we move on to the next slide. So here are the solutions to those. Sodium is 1s2, 2s2, 2p6, 3s1. If it becomes sodium plus 1, it loses 1 electron. And phosphorus is -3, so we lose these 3p electrons here. So we're losing those. I'm sorry, we don't lose those. We add 3 to that in phosphorus's case, and we get 6. Aluminum 2 plus would be, we'd lose 2 electrons, one of the p electrons and one of the s electrons. By the way, aluminum 2 plus is an uncommon ion. You won't usually see that type of ion. If we're looking at iron 2 plus, we lose 2 electrons, and here's again one of the weird things that we might not do so much of in Chem 130 is that when we have a transition metal ion, TM, transition metal ion, so if I have a TM neutral versus TM ion, the TM neutral says 4s 3d, a transition metal ion, because the charge changes, is going to have the 4s higher and the 3ds lower, which might seem to you the way it ought to be. So the electrons we actually lose are not the 3ds, we lose the 4s's because of that flip-flop that goes on like that to get the iron plus 2 ion. Samarium, again, this is down in the lanthanides and actinides blocks. Samarium plus 3 is going to lose 3 electrons, and it loses the 6s and one of the 4s. But again, these guys are probably not what we're going to be doing in Chem 130. Those are a little too complicated to deal with right now. Let's stick with the simple ones. Alright, so that takes us to the end of this little segment of the slides, and you'll be seeing some homework associated with that, and we will